Hello everyone, my name is Li Yue. I'm currently a PhD student from Peking University in China. This work I introduced is the FastBlock, which accelerating blockchains via hardware transactional memory. Where blockchain technology has been experiencing rapid growth in recent years, the post-threshold have significantly heightened the usability of blockchain with increased amount of users and transactions, where how fast a block is generated and confirmed determines the threshold of blockchain. Generally, the life cycle of a block involves four types: creation, execution, mining, and validation. Firstly, a block is created by a miner blockchain nodes, which collects the pending transactions and orders them to form a candidate block. Next, transactions enclosed in the block are executed sequentially to update local states. According to consensus protocol, every miner then tries to mine a block by making its own winning proposal. Lastly, the winning block is broadcast to other nodes in the network. Every single transaction in the block is then validated through a sequential re-execution.
Particularly, optimization of mining has been widely discussed in previous research works, including new designs of consensus protocol sharding and payment channel. There is relatively little study on improving the efficiency of execution and validation. We have AC, which enables concurrently execute more complex smart contract based off-chain execution model. Furthermore, there is another work which enables concurrent transactions in permissioned blockchain systems.
We proposed a blockchain framework called FastBlock to achieve acceleration of blockchain lifecycle via concurrent execution and validation of transactions. Firstly, we symbolically execute a given smart contract to identify minimal atomic sections for each function. Secondly, a concurrent execution step is introduced based on hardware transactional memory to process transactions concurrently without violating the atomicity of atomic sections. Next, FastBlock leverages the happen-before graph to schedule the concurrent validation. We highlighted the concept of the atomic section in smart contracts as a basic concurrent unit of the blockchain. FastBlock explores minimal atomic sections for each transaction to improve the degree of concurrency. Similar to atomic section in traditional programming languages, the atomic sections in transactions corresponding to code segments in the contract that operate the state. The table lists all access operations or states in smart contract. Based on the access operations, we define four types of atomic section in smart contracts to free smart contract developers from the burden of implementing correct concurrency controls and semantics for each smart contract. We leverage symbolic execution for automatically identify minimal atomic section in a given smart contract. Specifically, FastBlock takes a 3D source code as input and then generate the control flow graph for that contract via grouping instruction into connected basic blocks. Based on the safety, FastBlock symbolically executes all potential transactions. Then we generate a set of transaction scenarios with a specific bound. For each transaction scenario, FastBlock finds atomic sections of each transaction while checking whether their access operation matches the atomic section type.
Finally, FastBlock checks the scope of each atomic section. If two atomic sections overlap with each other in the same function, then merge them into one atomic section.
In the execution step of FastBlock, the miner concurrently executed transaction from the candidate block. Given a number of threads, the miner utilized a low-conflicting transaction selector to select the transactions from candidate block and then execute them parallel. The atomic section in transactions will be dynamically identified, and those instructions in an atomic section will be executed within the protection of hardware transactional memory to ensure atomicity. And then the miner sorts the transactions in candidate block according to the commit order in the candidate block from miner. The validation step is to re-execute transactions in that block and compare its final state with miners. With the transaction order from miner and predefined conflict information, validator firstly gets the atomic section for each transaction and reconstruct an happen before graph for all atomic sections. To ensure deterministic, the atomic section can be executed only if all its predecessors in happen before graph have been committed. In this step, validators do not have to worry about any concurrency control issues because the happen before graph ensures that the conflicting atomic sections will never be executed concurrently. Finally, the validator compares its states with the miners to decide whether the block is valid or not. Future work, we firstly plan to implement FastBlock on non-EVM-based blockchain such as US. Secondly, we aim to design a new programming language for smart contract which natively support threads and synchronization.